So again, welcome back to today's class. Today's class is about oil tanker calculation. This is only part one. So we'll be discussing about the basics, and then next week when we come back, we'll be doing one step further up. All right. So let's go to this oil tanker calculation. Now the target audience for this particular module are the candidates appearing for BSc Nautical Science, second mates, and also the phase one competency examination. Now we are going to go more or less competency examination oriented. However, the topic what we're going to be talking the first session is all about the basics. That's the properties of the oil and all that stuff. So it'll be useful for all others also, especially the engineers also, because they are involved in the bunkering operations, and then oil being oil, both bunker oil and the cargo oil both are same. So the calculations what happens in the bunkering operations are also same as what we do for the cargo calculation. At the conclusion of this module, the participants will be able to understand the effect of temperature on the volume, density, and the mass of oil. This is basically the heart of why we do all these calculations. The basic terminologies what are used on board with respect to cargo volumes. Then we also talk about various equipments what are used to determine the cargo volume in the tank. We'll talk about the correction factors, that is VCF, the volume correction factor, and the weight reduction factor. We will do some couple of simple examples using the ASTM tables, that is the tables used for oil correction factors and all. And we also do some calculations in cuboidal tanks without any list, without any train, a simple calculation. During the course of this module, we'll also be doing some basic numericals. So I request all of you to have a pen and a paper, and of course a calculator handy so that you can carry on with the calculation. Okay, so let's go ahead with this the first part of the oil tanker calculations. We look at the effect of temperature on the oil. Now, before we start the module, let us do a simple example. I mean, with this example, the whole fundamentals will be clear as to why we go about doing all these calculations. Let us start this experiment with a simple 1 liter of oil in a bottle. The mass of that oil is 1 kg. It is filled in a place, the ambient temperature is 15 degrees Celsius. That means the oil temperature is also 15 degrees Celsius. We keep it in the base as a reference, and then we start off our experiment. We are mainly going to concentrate on the volume part of it. So pay attention to the volume and then answer the questions. Now this is a level when the oil is at 15 degrees Celsius. So I'm going to put a small green line over there just for reference so that we know. So the black line is the base, the green line is the level of the oil at 15 degrees Celsius. Now the question to you is, we are going to go to a place which is colder than 15, that is about 5 degrees Celsius. When we go to that colder places, what will happen to the volume of the oil? In simple words, what we're looking at is what will happen to the level of the oil in the bottle. Will it increase or will it decrease or will it remain the same?
Decrease.
What would happen?
Decrease.
It will reduce.
Yes, please go ahead. Answer.
Decreases.
It will decrease.
Okay, this is common sense. This is what we observe in day-to-day life. That means when we go from 15 degrees Celsius to 5 degrees Celsius, when we reduce the temperature of the oil contracts, the volume reduces. All right. So what I'm going to do is I'm going to put a small mark over there, again a blue line, which signifies the oil is at 5 degrees Celsius. Now the next experiment, what I'm going to do is, we have this 15 degrees over there as a standard, so we are going to increase the temperature of the oil. Now what would happen to this oil with respect to 15 degrees Celsius? What will happen to this oil if we are going to take it to a place of temperature 30 degrees Celsius? Will the oil remain at 15 degrees or at 5 degrees Celsius, or what would happen?
Will increase.
Volume increases.
Volume will increase with respect to 15 degrees Celsius. So that is correct. That means the volume will increase when we heat up the oil. So now we have 3 reference points done over there. The first one is for 5 degrees Celsius. That is when we get the temperature below the reference point. That is when we put on the oil, the volume contracts, the oil contracts, and when we heat it up to more than 15 degrees Celsius, the oil expands. Now this is all known to us. This is something like what we know as a day-to-day affair. Now let us also look at the mass part of it. As I said, in the initial condition itself, the mass, the weight of the oil is 1 kg. That means at 15 degrees Celsius, the weight is 1 kg. Now when we move the oil to a colder climate, When we take it to 5 degrees Celsius, what happens to the mass? What is the change in mass?
There will be no change actually. Not
There is
significant.
no
No change in
No
mass.
change in mass.
no change in mass. Anybody else? Because there is something somebody is missing out. So anybody? Increase in mass or decrease in mass? Anything? See, after all, the oil is going from there's a change in temperature in the oil. So how about? Will it be the same or will it be
No change.
less or more?
Remain same, sir. Remain same.
Remain the same. Okay, very good. That means the oil, when we take it to colder climates, will still remain the same. It will still show as 1 kg. Now let us look at what happens to the oil again when we take it to a higher temperature. It is going to remain the same. That means the mass is not going to change, whereas the volumes will change. Now let us look at this particular part and let us analyze what is happening over here. When we have the standard reference of 15 degrees Celsius, when we take it to a colder place, let's say 5 degrees Celsius, when we lower the temperature, the volume shrinks, the volume reduces. When we take it to a higher temperature, a place with a higher temperature as compared to 15 degrees Celsius, the volume of the oil will expand. That means it will have more volume. Whereas when we talk about the mass always remains the same. That means there is no change in mass at all. The weight always remains the same. That means 1 kg at 15 degrees Celsius will still show, read as 1 kg at 5 degrees Celsius, will again show the same as in 30 degrees Celsius. Is it clear? Any doubts so far? The basics what we've covered so far?
No, sir.
No, sir.
All right,
Yes,
great.
clear.
So now let us look at the same experiment. Now that we have seen the change in the volume, the mass remains the same. Let us look at what happens to density of the oil. The same experiment, the same thing. So before we come into density, how do I define density? What is density?
Mass per unit volume.
Mass by volume.
Mass per unit volume. Perfect. Because short and sweet, that's what the meaning of density is. So we have the density as mass per unit volume. Now let us again do an experiment. Just let's get the hang of what is this density what we're talking about. I've got a ball of cotton wool over here on the left hand side, and I've got a ball bearing, stainless steel ball bearing on the right hand side. Now cotton is lighter, ball bearing is heavy. Is it not?
Yeah.
Yes, the
Yes,
volume being the same. Both the volumes are same. If you see the circular dimension, both are almost same. But the cotton is lighter and the ball bearing is heavier. So if I ask you a simple question, which has got higher density, cotton or the steel ball bearing?
Steel ball bearing.
Steel ball bearing. That means I've got more mass packed up into unit volume, and that is why the ball bearing density is higher. Whereas the cotton, which is same volume but it's very fluffy, it's got full of air inside. Even though they have the same volume, the cotton is lesser density and the ball bearing has got higher density. Is it clear? Now the unit of density, as the definition says, it's mass per unit volume. Now what is mass measured in?
Tons.
Tons. I can also measure it in kg. So there are like either tons or kg. That's what the normal common terms used in the normal denominations. What is the measurement for volume? Unit volume. So how do I measure unit volume? What units would I measure it in?
Meters per meter.
Ton per meter cube.
No, ton per meter cube is for density, but for the meter cube is a unit volume. That means it can be a meter cube, or we can also say it in per liter also, because again liter is the same as unit. I mean, it's a unit of a volume. So we can either have mass per unit volume, that is mass in tons, or unit volume. We can refer it as cubic meters, that is ton per cubic meter. This is what normally we shippies are all used to, tons per cubic meter. The same thing can also be referred in kg per liter. Now, if you actually see the units wise, the tons, we're reducing it by 1000, I'm getting it kg. Cubic meter, I'm reducing it by 1000 units, I'm getting it 1000. 1 liter. That means if I have let's say a particular figure, if I mention it in kg per liter or mention it in tons per cubic meter, both units remain the same. I mean, the numeral remains the same. The unit may vary, but then whatever, let us say if I say 0.8 tons per cubic meter, that's also same as 0.8 kg per liter. Is it clear? Any doubts there?
Yes, sir. Clear.
Okay, all right. Now we have defined the density as mass divided by volume. So what we're going to do is, keeping the mass on one side, If I take the volume on the left hand side, we will have mass is equal to density into volume. This is the kind of like what you call the calculation what we use for a tanker for finding out the mass. So mass, that is weight, is volume multiplied by density. Now one thing we have to remember very clearly is over here, as we saw in the previous example, the volume changes with temperature. All right. So we have to be very clear when we are referring to this particular equation, mass is equal to volume into density. Both volume and density have to be at the same temperature. If I use a volume at a different temperature and density at different temperature, then the mass which is calculated is not correct. Clear? So let us look at the effect of density on the oil, density of the oil when the change of temperature happens. So this is what a previous example was. We have different volumes at different temperatures. 5 degrees is the least, 15 is the standard, and 30 degrees is more than 15 degrees. Whereas the mass remained the same. This has got low. At 5 degrees, the volume shrinks. That means the volume becomes less for the same amount of mass. That means the oil density increases. For 15, it's a standard reference. So we skip 15, we come to 30 degrees Celsius. Now here the volume of the oil has expanded. The volume, the oil has kind of like expanded, but then retaining the same mass of 1 kg. That is why the density reduces. Clear? So let us summarize what we've done with a simple example. If I have a given volume of oil, the temperature is reduced, the volume reduces, and the density increases. The temperature of the oil is directly proportional to the volume, but indirectly proportional to the density. The temperature comes down, the volume comes down, whereas the density increases. Conversely, if I increase the temperature, the volume increases because the oil expands, and because the oil expands, the density reduces. Now, the standard temperature what we use for all our calculation is 15 degrees Celsius. Of course, world over, there are a lot of other temperatures. But as I said in the beginning, this module is mainly for MMD examination, the kind of the questions which come in MMD competency examinations or in the IMA examinations. That is why we are sticking to the standard references as 15 degrees Celsius. If you actually on board, if you go to like places like US and all where they use at different units, we may also use something like 60 degrees Fahrenheit and all. Some countries in the world also use 20 degrees Celsius for their standard reference. But as this module is based on the MMD examination, we will stick to 15 degrees Celsius. The mass always remains the same. There is no change in the mass at all because we are not changing anything in the mass. If the volume increases, the density reduces, and the volume reduces, the density increases. So they both compensate each other, and that is why the mass always remains the same. The unit of density is tons per cubic meter or kg per liter. And finally, the formula for the mass, that is the weight, is volume into density. Again, remember, the volume and the density both have to be at the same temperature. If the volume is at a different temperature and the density is at a different temperature, the answer will not be correct. So the density and the volume has to be always at the same temperature for formula at number 6 step to be used. Mass is equal to volume into density. Any doubts, any queries in the small example what we did? Because this forms the basics of your oil calculation. If you're comfortable with this particular part, that means we can visualize what really happens when we go from a colder climate to a hotter climate, or when you take a bunker from, let's say, in Fujairah or in Singapore in the afternoon. What happens to the same oil in the colder climates or maybe in the nighttime? So this is what really is the basis of the oil tanker calculation. Any questions so far? Let me see if anything is there in the chat.
Moderator here, sir.
Yeah, hi, good afternoon.
Captain Subramaniam Anand, sir.
Yes,
Mr. Sandip had raised that he need to view the previous slide. I think he having some doubts in the previous slide.
Okay, Sandeep, can you tell me which slide I'm going back? Sandeep, you're there? You can unmute yourself. It's an interactive session. Please unmute yourself and speak up.
Sir, one slide back. I need to
slide back. Okay, this one?
No, sir. The next slide.
The previous slide, you mean to say?
The next slide. Next slide.
Next. Okay, subsequent slide. Okay. After this. This one?
Sir, I think he wants the calculation part.
Okay.
Calculation part. Yeah, right.
Slide number 8 he wants.
Slide number 8. Okay, all right. Okay, the
Yeah,
summary of it. Yeah, summary.
Yeah, summary of it.
Okay. I'll get all of them. Yeah. All right.
Okay, sir. Thank you.
Great. Good to go. If you understand these basic concepts, all the oil tanker calculations, you can actually visualize what really happens in the oil compartment. So this forms the basics of the oil calculations, especially as far as the MMD examination is concerned. If we can kind of visualize what really happens inside the oil compartment, then half the battle is won. Clear? So we go to the next chapter. We'll be talking about few terminologies what we use, because tanker people are a breed apart. So we will use some terminology, some kind of like terms what we use to refer to some kind of volumes or some kind of the oil content what is there in the tank. So let us talk about some things. Now, total observed volume. This is called as POV. All right. Now let us look at this picture over here. We have a picture of a tank which is full of at least like most of it is full of oil. The oil is brown in color. And now if you see in the bottom there is some water. Water is like higher density than the oil, so the water always will float. I mean, it will go to the bottom. The oil will be staying on top. And you see these green things are the sediments. The sediments are like sludge. They come along probably like when we load these crude oils and all. May not be prevalent in the product tankers, but then it's very, very common in the crude oil tankers. So when we talk about the total observed volume, we're talking about the total volume in that tank at that given time at the observed temperature, because again the observed comes in, that means at the given temperature, that means at the temperature at which it is outside, not the standard temperature, the ambient temperature. So now what happens is, if you find out the total volume of the tank, the total observed volume includes the volume of the water, includes the sediments, includes the sludge, includes all these impurities which are there in the bottom. Clear? Now this is measured at the observed temperature. When we come to the next one, that is the gross observed volume. The gross observed volume is minus the water and minus the sediments. That means total had the water and the sediments. When we come to the gross observed volume, we exclude the water, and we exclude the water and the bottom sediments. That means finally what I have is only the oil. See, what happens is when we have this water in the bottom of the tank, now the charterers are not going to pay for this water. The water is free water. The water is freely available at the sea also. So we are not going to be paying the freight for these water. The bill of lading will not include this free water which is lying at the bottom. So this is excluded in all the tanker calculations for freight calculations, and also we don't want to calculate this water content. That's the reason for changing over from total observed volume (TOV) to gross observed volume, that is GOV. That is only the oil which is there in the tank. We also have one more thing called standard gross standard volume. That means what we do is the next step from this gross observed volume, what we do is we go one more step further, and then we define that as this gross observed volume is at observed temperature. That means at the prevailing ambient temperature. Whereas when we talk about the gross standard volume, we come to a standard temperature as 15 degrees Celsius. You saw in the previous example also the volume keeps on fluctuating if we change the temperature. So for us to go ahead with the calculations, we have to have a standard volume at a particular standard temperature. And standard temperature, what we use world over for the tanker calculations, is 15 degrees Celsius. So gross standard volume talks about the volume at 15 degrees Celsius. Clear? The next part is about the content of the oil inside the tank. Now when we are talking about discharging operation, discharging is almost finished. There is still some amount of oil in the tank which we cannot discharge. These are like either unpumpables, because you can't discharge the pump can't reach those pockets of oil which is there in the tank. This is when I talk about ROB, that's remaining on board. We're talking about all the unpumpables which is there inside the tank after the completion of the discharge activity. This is very important. You cannot discharge this with the fixed pumping arrangements on board. If you put a portable system, that's a different story. But the fixed pumping system, with the fixed piping system of the tanker, you cannot discharge them. These are called remaining on board. This is always taken up, calculated towards the end of discharging activity in the discharge port. Can anybody tell me why do we need to calculate for this ROB? Why should the charterers or why should the agent be interested in finding out how much of oil is left in the back of the tank?
The percentage can be calculated for the next calculation purpose. So VF.
Okay, we will not talk about VF right now. We are just about the basics only. Why would this be required? be calculated?
For the calculation purposes. For
calculations, can you please elaborate? You're partly correct. Calculations, yes, but why?
the amount what we have discharged.
To get the total volume of the oil.
Volume of the tank.
See, now the freight is being paid for you to discharge the full oil. What will happen if I collect the freight from the charterers, saying that I've carried the oil from place A to place B, but I have retained half the oil, half the quantity of oil inside my tank, saying that it's unpumpable. That means whatever oil is at the bottom of the tank, what is not discharged, the ship owner is not, the carrier is not going to get the freight for this volume, which is here, because that's a loss for the charterers, for the shipper, and that is the reason why we calculate this quantity towards the end. Now the same ship is going to a load port. In the load port, she arrives with this quantity of oil at the bottom of the tank, and now that is what is called onboard quantity. The quantity is the same. You see, there is no difference between what is there in the ROB and what is there in the OBQ. But here, only the terminology has changed. What we mention here is onboard quantity. Instead of saying remaining on board after completion of discharge, what we say is that onboard quantity before we started the loading. So when we talk about OBQ, we're talking about something which is already in the tank. So, and this is from the previous discharge operations, and it is declared in the load port prior to the start of loading activity. So before we go for loading activity, there's something called tank inspection. There they find out if any oil is there in the tank. If all tanks are all zero, that means we say zero OBQ. And if on the completion of the discharging operation, if all the tanks are clean, that means there is no content of the oil inside. We term it as zero ROB. Clear? So these are the various terminologies what we use. And again, we are only sticking to our examination purpose. So we stop at these five basically. We talked about GOV. We started first with TOV. Then we talked about the gross volume, and then we talked about this standard volume, and then OBQ and the ROB. Now, let us come to the heart and soul of this oil tanker calculation. That means what we are going to find out is we are going to find out what is the volume of the oil in the cargo tank. Now, the basic condition is that the tank has got no list and no trim. That means it's perfectly even keel and perfectly upright. In that case, what we do is we find out what is the gross amount of volume in the tank. And for finding out the volume, like I said in the previous example, there are some equipments what is used. The first one is a sounding tape. The same can be used. Sounding tape is normally used even for bunkering also. So something similar, the sounding tape. That means what we do is we have a sounding tape. It is put in a sounding pipe, and the sounding tape goes all the way down. There's something called an oil finding paste, which is applied on the tape. And the oil finding paste, like water finding paste, it changes color only when it touches the oil. Nothing happens to it when it touches the water or when it is in the air. It only changes the color when it is touching the oil. That means when we put the sounding tape inside, we come to know the depth of the oil directly. Now that is called as sounding tape. Next is called allege tape. Now sounding tape, the problem is, and we are going to put the whole tape inside. Again, when we pull up the tape, a lot of oil will come in all this, what is sticking onto the tape will come onto to this roll. So what we find out is we are not interested in finding out what is the depth of the oil. What we'll find out is how much of the empty space is there on top. That empty space is called allege. So this tape is called allege tape. It is also known as sonic tape, ultrasonic tape, because the fundamentals what is used is the ultrasonic frequency and the conductivity of this oil. That means the bob will be hung from top. As soon as the bob touches the water, there is an alarm which comes in because the conductivity changes. The conductivity of the air is different and the conductivity of the oil is different. So this is what is called as an allege tape. It can also be used for finding out the interface. We saw the previous example where we want to find out how much of water is there in the bottom of the tank. So to find out how much of water is there in the bottom, we can use the same tape, and then the tape is called UTI, allege, temperature, and interface. So it gets the interface also, and then it gets the level also. Now next one is, again, there's a fixed system. What we have something like a radar. The radar signals, that is electromagnetic signals, is sent down. The beam of signal goes down, it touches the level of the liquid, it's bounced back, and then the radar picks it up. The difference of time, like an echo sounder or like a normal navigation radar, the difference of time between the pulse sent out and the pulse received is the amount of allege. So whatever distance is there, we divide it by 2, then we get the amount of allege from the tank top. So this system is called radar gauge. We also have one more very, very old system. If you've sailed on those like 20 plus years old tankers and all, you will find this system, what is known as float gauge or vessel gauge. In this, we have a float system. It's a spring-loaded system where it is the spring is. There's a float at the bottom of this gauge. The float keeps on going down. When the float touches the level of the liquid, it cannot go down any further. And this Verso gauge, there's a meter inside which maintains a constant tension in this spring. So as soon as it touches, it maintains a constant spring. We come to know how much, where is it when it has touched the surface of the oil, and that again gives us the ullage. So these are the four equipments what we use on board a ship for finding out the ullages or the soundings. Ultimately, what I want is we want to find out what is the depth of the oil. So from ullage, we subtract the depth of the tank, and we come to know what is the depth of the oil which is inside. So far, so good? Clear?
Yes, sir.
Yes, sir.
Understood?
Yes, sir. Thank you.
Yeah.
Yes, sir.
Now, using any of these methods, ultimately what we want to find out is the depth of the oil in the tank. Clear? And once we know the depth of the oil, it's a simple calculation, simple volume calculation. That is, we know the breadth of the tank, we know the depth of the oil, and we know the length of the tank. So volume is basically length into breadth into depth. A simple calculation, which is there. Now, can we find out the oil? How much of oil is there in this tank? I've got an example over here. Please take out a pen and paper and a calculator. Or some. I don't think we need a calculator for this question. The depth of the oil is 10 meter. The length of the tank is 20 meter, and the breadth is 15 meter. How much of oil is there in this tank? And again, the tank is upright and even keel. That means there is no list, there is no trim. It's a
3,000, sir.
How much?
3 cubics.
3,000 meter cube.
3,000 meter cubes. Somebody said 3 cubics. It is 3,000 cubics. It's a simple multiplication of 10 into 20 into 15. That gives us 3,000 cubics. Understood? So once we know what is the depth of the oil in an upright tank, that is what is the most important thing. The finding out the volume is a straightforward multiplication with the length and the breadth of the tank. Clear? So when we talk about the oil tanker calculation, again we'll be going on to these basics. So this is what we have studied way back in our 5th standard, 6th standard or something. And this again we have to scrape up our knowledge and then get on this information. Now this is for examination purpose. Can somebody tell me how do you obtain the volume of oil or water in a tank on board a ship? Do we really calculate the length and breadth of the tank? Of course, we do calculate the depth of the oil or the ullage of the tank, but how do you go about calculating the volume of a tank on board a ship?
Ullage tables.
Ullage tables, very good. So we have sounding tables, ullage tables, which is pre-calibrated, and it is done in the shipyard by the naval architects. They know exactly how much of what is the shape of the tank and how much of the various obstructions in the tank, and then they give us this calibrated table. So we have something called as an ullage table or a sounding table, which gives us this volume. Okay. Any questions so far? In this, it's a very small topic. What we talked about the volume of the tanks. Anything in this part?
No questions in chat, sir.
Okay, great. Again, this was very basic, so let's get on to the fundamentals now. All right. Now we talk about the volume correction factors. Okay, this is when it gets a little more interesting. So you need your attention here. We notice in chapter 1 with our example with that bottle of oil. For a given amount of volume of oil, if the temperature is reduced, the volume reduces and the density increases. Yes or no?
Yes, sir.
Yes.
Yes, sir.
And conversely, the temperatures increase, the volume increases and the density reduces. We also saw that what is the formula for this mass or calculate the weight of the oil in the tank? Volume into density, provided the volume and density are the same temperature. If they're not in the same temperature, we have to convert them into same temperature. And that is what is the oil tanker calculations about. So the life is not so simple. So we'll have volume in a different temperature, density in a different temperature. So what we'll do is we will get everything into a standard temperature. And then we can apply this particular formula. All right. So let's get on to this, the further steps in the oil tanker calculations. Like I said, we have to ultimately find out what is the mass, what is the weight of the oil which is loaded, which is used in a loadicator, which is used for our bill of ladings and for fighting for those figures with the bunker barges or whatever it is. So we ultimately what I need is a metric tons amount of weight, what is there, what is loaded. The weight is actually calculated by volume into density. Volume I've showed you exactly how it is done. But again, remember, both have to be at the same temperature. The density is given by the cargo surveyor. So we will look into this density part also as to how it comes about. So here the problem is we have a density at a different temperature and the volume at a different temperature. So we are going to be correcting the volume to a temperature, that is the volume at the observed temperature to 15 degrees Celsius. Once I get the volume at 15 degrees Celsius, the density is also at 15 degrees Celsius. Now we can easily multiply these two and get the mass. Is it clear? So that's what we are going to do. The standard temperature, as I said earlier, is always 15 degrees Celsius. The density is always provided in this temperature also. We will come in the next slide, we will come to know more about this density part of it as to why we selected this particular temperature. If the volume of the oil, which is calculated after finding out the ullage or the depth of the oil and all, is other than 15 degrees Celsius, if it is different from 15, the volume of the oil has to be corrected to 15 degrees Celsius. Clear? And for this correction, what we use is a book called ASTM Table 54. This ASTM stands for American Standards of Testing and Materials. Now this is it's a very it started off almost about 160 years back. They have been calibrating all these tables for various calculations. So we have ASTM tables for gas, for lube oils, for paints, and all for all these things. They also supply the tables for the calibration tables for oil calculation. A lot of tables in which specifically what we use is for table 54 for this correction. So we will be referring to those tables in our examples also now, which are coming up next. It is entered using density of the oil at 15 degrees Celsius and observed temperature. So we will do a couple of examples of this, and then we will see how it is very simple to calculate this particular part of it. So this is an extract of an ASTM table. Again, remember, this is an exam copy. On board a ship, what we have is ASTM table A, B, C, D and all. And what the product tankers use is table 54B. What the crude oil tankers use is table 54A. Whereas for examination copy, it is just table 54. Clear? So this being a module only exam oriented, we'll be sticking on to table 54. Now there's something called a small booklet comes in. It's an exam copy, it's an extract of the ASTM tables. And that is used for the MMD examination. Clear? Clear so far?
Yes, sir.
Yeah. All right. So let us take some examples out of this. And the unit what is mentioned inside is kilogram per liter. Kilogram per liter, like I said earlier, is also same as tons per cubic meter. If I multiply the numerator, that is kilograms, into 1000, and the denominator also into 1000, what we get is tons per cubic meter. So whatever unit comes in, they're both interchangeable. The same thing can be used. And again, I'm telling you, this table 54, what is there, what we're going to use for examination, it's only for exam purpose and not for onboard use. For onboard, we have a separate booklet, which is called that ABCD and all, which is a different thing. This is an example of an ASTM table. I'm just giving a layout. So let us look at how to read the values. On the left-hand side, we have observed temperature. Now, what is the purpose of using an ASTM table 54? It's a volume reduction. That means volume. I'm going to convert the volume to 15 degrees Celsius. Like I said in the earlier, mass, the weight is equal to volume into density. We already have the density at 15 degrees Celsius, but the volume is at an ambient temperature. It could be 35, it could be 30, it could be 15, it could be less than 15, 5, 10, depending on which place you're loading the oil from. So our intention is to, before we use a formula, we all have to get it to the same temperature. So what we find it easier is to convert the observed volume into volume at 15 degrees Celsius. That's our goal over there. So what we have is the observed temperature on the left-hand side and the various densities. This density is provided to us in the certificate of analysis, in the quality certificates of the oil what is loaded, or the bunker barge persons will give us this density of the oil. So the density of the oil is always at 15 degrees Celsius. So on the top, what we have is 15 degrees Celsius, and on the left-hand side, what we have is the observed temperature. Clear? This is how it is. That means let us take up an example over here. If the density at 15 degrees Celsius is 0.795 kg per liter, find the VCF at 5 degrees Celsius. So how do we find out the VCF now? Using this table. The density is 0.795, that is this column. The observed temperature is 5 degrees Celsius, that is this row. So how do we find out?
10092.
0092. So it's very simple. What we do is we first go to the 5 degrees Celsius. We put a scale over here. We take it around on this on the same horizontal, and then we stop at where we reach this temperature density, the density of at 15 degrees Celsius. From there, we'll start looking down. So wherever these two meet, that the value is 1.0092. So the volume correction factor is 1.0092. I request you guys to please note it down somewhere on a piece of paper, because we'll be using this VCF for our simple calculations further down in this module. All right. So let's now look at let's take up another example over here now. Now the first example what I took was less than 15. The second example what we are going to take is more than 15 degrees Celsius. So the observed temperature of the oil is more than 15 degrees Celsius. So now can somebody tell me what is the VCF if the observed temperature is 32 degrees Celsius and the density is 0.800 kg per liter or tons per cubic meter?
9854.
9845.
9854 or 9845?
9845.
9845. So again, the procedure is simple. We keep the horizontal row 32 degrees at the same temperature, the observed temperature, and the density is 0.800, and where they both meet is 9845. Practically also, and also for example, please use a scale, because we should not make a mistake in going up and down, especially when you reach towards distance far away from the temperature. You may go up and down, especially if it is hidden in the middle somewhere. So this is how it is taken. If the temperature or the density is between somewhere and between, then a simple interpolation has to be carried out. So I'm not going to go into the interpolation part, because it is same as your hydrostatic tables interpolation what we do. So I'm not going to be taking up the interpolation part over here. It is assumed that the interpolation part is known at the level at your competence. So the VCF comes down to 9845. That is what is these two meet. And please note it down also, because we are going to use the same value again in our next example. Now it's a simple. Now last one is. Sorry,
Sir, one doubt.
Yeah.
Yes, there are a few numericals beside to these values actually.
Okay,
1,
I'll explain
1,
it to you in
2,
this slide itself. All right. So this is basically used for interpolation. Now let us look at this number over here on the top, the topmost row. What is the difference between this number and this number? 1.0122 and 1.0120. What is the difference between these two?
2, sir.
Okay, let's look at this one. 1.0083 and 1.0083. Any differences there?
Nil, sir. 0.
Nil. Okay, so that's a difference between the two numbers, which we basically use for interpolation. So now looking at the number, if the density is anywhere in between, if the value is 0, I can blindly put the same number, because there is no change across the densities. We need to actually do the interpolation only when the number is other than 0. It's basically for the use of like ease of work. Okay, so the third example what we are going to do is at 15 degrees Celsius. The density of the oil is 860. The VCF, the observed temperature, is also 15 degrees Celsius. What will be the correction factor which is used?
1.
Why is it 1? How can the correction factor be 1? What does it mean?
Because the temperature is already 15 degrees.
Yeah, the observed temperature, the ambient temperature and the standard temperature are both the same. That means there is no reduction, there is no increase in the volume. The volume is the same. That is why, if you see over here, the 15 degrees, all the numbers are all 1. So we still go by this practice. So we take it from 15 degrees and we come around the density, and then we get the value for 1.0000. So VCF is 1. There is no change in the volume, because your observed temperature and the standard temperature are both the same, and that is why there is no change. Okay, now with the same table, let us look at the correlation of the VCF and the temperature. This is very important, because sometimes in examination or even on board use also, we calculate one factor. So how do we know that the factor is like approximately correct or not? Let's look at the factors which are less than 15 degrees Celsius. 15 degrees is out over here, which is 1.0000. Any factor which is less than 15, what are the numbers you see over here? It's all 1 decimal something, is it not? 1.00, 1 point something something, 1.01, is it not?
Yes, sir.
So if the temperature is less than 15 degrees Celsius, the factor, the VCF, the volume correction factor, will always be more than 1. if I have to use it in the common simple words, see the temperature is less, observed temperature is less. Let us take at 0 degrees Celsius. If I have an oil at 0 degrees Celsius, now I'm going to heat up the oil to 15 degrees Celsius because my standard is at 15 degrees Celsius. What happens to the volume of the oil when I heat up the oil go from 0 to 15? The oil will expand? Yes or no?
Yes, sir. Yes,
Yes.
sir. Yes.
If the oil has to expand, we have to multiply by a factor which is more than 1. That is the reason why for a factor of for a temperature which is less than 15, the factor is always more than 1. Clear? So even by mistake, if you calculate something by mistake because of the heat of the moment or because of the confusion or that the stress, examination stress or onboard time pressures, for a temperature more than 15 degrees or for a temperature less than 15 degrees, if you put 0 point something something less than 1, that means that itself tells you that the factor is wrong. Okay, so always remember less than 15, the factor is always more than 1. Why? Because you're going to heat up the oil to reach 15 degrees. If you heat up the oil, the volume will expand. Clear? We already discussed 15 degrees Celsius, the factor is always 1. Now let's go to the next step. If it's more than 1, if it's more than 15 degrees Celsius, what we're doing is we have to shrink the oil. That means we have to condense the oil. And that is why if the temperature is more than 15, the factor will always be less than 1. You will see over here the factors are 0.9988, 0.9845, whatever be the numbers, what comes in. So less than 15, factor is more than 1. Equal to 15, the factor is 1. The temperature is more than 15, the factor is always less than 1. Is it concept clear?
Yes, sir.
Okay. All right.
Yes, sir.
Now let's do some examples over here now. Now right now what we're going to do is only converting the temperatures. Correcting the volumes only to the temperature. Okay. So what we have is the first example. Find the corrected volume at 15 degrees Celsius if the density at 15 is 0.795. The same example what we used earlier also. So you can take the same factor from there. So the observed temperature is 5 degrees Celsius, and here the new concept what is added is the observed volume, which is 2500 cubics. So what we have to find out is the observed volume at 5 degrees Celsius is 2500. What would be the volume at 15 degrees Celsius? So how do we go about doing it? We have the volume correction factor as 1.0092. If you remember the previous example, what we have already calculated, the observed volume is 2500, which is given in the numericals. So we multiply these two. That means we are going from the observed volume to standard volume. That is why from GOV we come to GSV, that is gross standard volume, at 15 degrees Celsius. Anywhere this S comes in, it always stands for 15 degrees Celsius. So we multiply these two things, the volume into the correction factor, we get this thing of 2523. Is it clear?
Yes, sir.
Now take a step back and just see what I've done. The temperature of the observed oil is at 5 degrees Celsius. So when I convert from 5 degrees Celsius to 15 degrees Celsius, what happens to the volume of the oil? Will it shrink, increase or decrease?
Increase.
Increase. Now after the calculation, has the volume increased?
Yes.
Yes, that means
Right.
more or less your factor is correct. That means from 5 degrees Celsius, if I heat up the oil, the volume will increase to 15 degrees Celsius, and that is why the volume is more. Is it clear?
Yes, sir.
Now let's take a next example again. The example what we did a few minutes back. Here we have to find out the volume at 15 degrees Celsius. The density at 15 degrees Celsius is 0.8 kg per liter, and the observed temperature is 32. That's what we did just a few minutes back. And now here the observed volume is 1500 cubics. What is the ambient temperature? What's the ambient temperature of this oil?
32.
32 degrees. So from 32, we have to take it to 15. That means what are we doing to the oil? Are we going to expand the oil or condense or contract the oil?
Contract the oil.
Cooling means the contraction. That means we are going to be making it lesser in size. And the working out exactly same. This VCA we've already calculated from an example, 9845. The observed volume is 1500. So multiply these two and you get 1476. And again, before we go to the next step, just go one step back and just see. At 32 degrees, the volume is 1500. Now, when I cool it to 15 degrees Celsius, the temperature comes down. That means the volume reduces. Is the volume reducing over here from 1500 to 1476?
Yes, sir.
Yes, sir.
That
Yes,
means
sir.
the job done. That means your calculation is more or less correct. At any one point of time over here from 32 to 15, if you see the volume is going up, that means you used the wrong factor. Either you used a factor which is totally different or maybe from some other factor you used it. So at this step itself, you can correct yourself before you proceed down to the more complex calculation. And now here the last example, this just for like what you call simple sake. Both the observed and the standard temperatures are the same. Any change in the observed volume?
Oh, sir.
No change, because
No change.
the VCF is 1.000. That means there is no change at all. Clear?
Yes, sir. Clear.
Yes, sir. Yes, sir.
Okay. So now let's look at the density of the oil. I mean, how we go about doing this. Little bit about the background information. What is given over here? The density of the oil is given by the cargo surveyors. Same for bunkering also. When you go for bunkering operations, the bunker barge, the cargo surveyor, they will be giving you this the density. The density is always measured in the shore laboratory in a very standard atmosphere, standard climates and conditions and all, and using standard measuring parameters so that uniform results are always obtained. And that is the reason why the density in the lab is always in vacuum and at 15 degrees Celsius. This is very, very important. The density what the surveyor gives us is always in vacuum and at 15 degrees Celsius. This 15 degrees part we already seen it, but this vacuum part we didn't pay much attention to it so far. So we'll look at a little bit on this vacuum part of it. But the standard temperature is always 15 degrees Celsius. All right. So why vacuum? Because again, like I said in the point number 2, the laboratories are all done in very standard atmospheres and standard climates and conditions, and that is why it is measured in vacuum. When we measure this, when we use this formula, mass is equal to volume into density. If this density is in vacuum, the mass will be also in vacuum. That means the mass obtained, the weight of the object obtained also will be in vacuum. So, but then the problem is we don't want the mass in vacuum. We want the mass in air. The ship is in the air. The cargo is in the air. I mean, the bill of lading figures are all based on the air. The load indicator figures for your alleged reports, all those figures are all based on the mass in air. So we don't want the mass in vacuum. Clear? And so we have to use another table called table 56 to convert the weight in vacuum to the weight in air. All right.
Captain Anand, sir, sorry for the interruption.
Yes.
7 minutes left, sir.
7 minutes left. Yeah, thank you.
Yes, sir. Thank you.
Yeah, right. So what we're discussing about is to convert from vacuum to air. The density is always given in vacuum and 15 degrees Celsius. Even in the examination, even if the survey does not tell you it is vacuum and 15 degrees, it's always understood that it is always in vacuum. So we don't cross question them. It's always in vacuum and 15 degrees Celsius. If I measure this density and calculate my mass, the mass will be in vacuum and not in air. What we need is the mass in air and not in vacuum. So what we use is a table 56. Again, like table 54 is a separate table. What is there in the ASTM booklet. And what we use, there's a table what we use to convert from weight in vacuum to weight in air. There's always a reduction factor because when we will come to the next slide, we will understand why we apply this factor. Now the air is, the air is surrounding this Earth's the Earth's atmosphere, whatever is there. It's an envelope of air which is a fluid. Any fluid will exert what is called as buoyancy. So all fluids, including air, also water, exerts an upward thrust on all the objects inside within it, and that is what is called a buoyant force or buoyancy. Now the approximate density of this 1 cubic of air is about 0.0011. So it can be either calculated using this table 56, or the most simplest thing what we do on normally what the practice what we follow on board is whatever is the density in vacuum, we subtract 0.0011 and we get this. We can convert the density in vacuum to density in air. So when I convert this density in vacuum to density in air, the density in air when it's multiplied by the volume, what we get is it mass in air or mass in vacuum?
Mass in air, sir.
Mass in air. So ultimately, what we need is mass in air. So let's look at this particular, and this is very commonly done on board. On board, we very, very rarely use this table 56. We directly just do this like subtraction of whatever density is given minus 0011 we do, and then we get our density in air. The density in air multiplied by the volume, standard volume, will give us the mass. All right. So now that we are doing this this module, let us look at ASTM table 56. It looks like this. On the top, you see density at 15 degrees Celsius, and on the side over here, we get factor for converting weight in vacuum to weight in air. So we can do it by both the ways. In examination, if you wanted to use this, you're free to use it. But then this is you're introducing one more element of uncertainty over here. If you pick up a wrong factor from top or from the bottom of this table, again the whole thing is lost. So the easiest way is to measure by using the density in air by just subtracting 0011 from the density in vacuum. All right. So given an example, density is 0.795. So what would be the factor in table 56? So we look at this table over here on the left hand side.
865.
Yeah, so the table, this thing comes in over here. So this 0.795 lies between these two figures. And so the number is 0.99865. Again, please note it down because we'll be doing one more simple example, simple corrections to find out what is the mass of the oil. Okay, so let's work out this particular equation, this particular numericals. Some of the values are you already have it from your previous the examples what we did. Find the weight of the oil if the density at 15 degrees Celsius is 0.795 and the observed temperature is 5 degrees and the observed volume is 2500. Earlier we calculated the standard volume GSV. Now what I want is we want the weight of the oil. So what we do is in the first step what we do is we find out the GSV. That is the gross standard volume, the volume at 15 degrees Celsius. How we go about doing it is find the VCF, which you already have, and the observed volume, and you multiply these two, we get the gross standard volume, GSV. That is the first step. First step is to find the GSV, the 2523 cubics. The next step is to find the weight in vacuum. The weight in vacuum can be found in two methods. We will use both the methods and see how close they both are. First is getting the weight in vacuum is we are going to multiply this GSV by the density in vacuum. So whatever value you get over here, the multiplied by the density in vacuum, we get what is called as a weight in vacuum. Can we use this weight in vacuum for our calculations directly for load indicators or for bill of lading figures?
No, sir.
No. So what we need is we want to find out what is the weight in air. In our examples, what we have found out is the WRF is the weight reduction factor is 99865. Yeah. So what we do is again we multiply the weight in vacuum by this WRF, that is this figure over here, 2005 decimal 785 into the WRF. The final answer what we get is 2003 decimal 077. That is the weight in air. Clear? So the final answer is 2003 decimal 077 tons in air. Any doubts in this calculation what we did?
So one more time.
Okay. What we want to find out is the weight of the oil. See, ultimately, I want to know weight of the oil. Even if you go to the market to buy any vegetables, I want to buy 1 kg potato, 1 kg tomato, whatever it is. But it's all weight in air. We don't want the weight in vacuum. So the first step what we do is we find out the GSV. From the given values, we find out the GSV. Now, GSV means what? I have to convert the volume at the observed temperature, temperature being 5 degrees Celsius. I have to convert it to volume at 15 degrees Celsius. That is what is called the volume correction factor. Now, in our examples, what we found out is for this 5 degrees Celsius and this density of 795, the VCF happens to be 1.0092. So, to find out the volume at 15 degrees Celsius, multiply these two numbers, 2500, that's the volume at observed temperature, multiplied with the VCF at that observed temperature, we get a figure of 2523. So far, so good?
Yes, sir.
Yes, sir.
All right. Now, the next one is weight in vacuum. Now, we have to find out, there are two ways, like I said, two ways to reach this weight in air. So, the first step is using the WRF. So, next step, what we do is we find out the weight in vacuum. So, weight in vacuum is what? Again, the simple multiplication, that is GSV, that is what we found out at step number 1. Multiply by the density, whatever density surveyor is given, we directly multiply by the figure. We get a value of 2005 decimal 785. Now, is it in vacuum or is it in air?
Vacuum, sir.
It is in vacuum because the density what I've used is is density in vacuum. That is why the answer what is obtained is also density in the weight in vacuum. Now the step 3 is to convert the weight in vacuum to weight in air. Now what table do we use for this? ASTM table, which table number?
56.
Table 56. So table 56, we get this WRF, the weight reduction factor. Again, it's a simple multiplication. Weight in vacuum, which is obtained over here, multiplied by WRF, what is obtained over here. Simple multiplication of these two gives me an answer of 2003.077. And now that is the weight in air. Now you see what happens over here. The weight in vacuum is 2005. The weight in air is 2003. It's a reduction. That is why this WRF is always weight reduction factor. We never go beyond what is vacuum. Vacuum is a maximum. Because you're putting it in air, the density, the buoyancy of the air reduces the weight of that the object which is there in the air. That is why the WRF is always called as a weight reduction factor. Whereas when we talk about the volume correction factor, we don't call it as volume reduction factor because it can be reducing, it can be expanding. Like in this case, it has expanded the volume. In the cases where we go more than 15 degrees, it will reduce the volume. Whereas the weight reduction factor is always less than 1. So don't ever make a mistake of putting the WRF more than 1. It will never be more than 1. Clear? It will always be less than 1. So finally, when you do an answer, when you find out the answer, just do a mental comparison between these two as a volume reduced. If the volume is reduced, more or less, your steps are correct. That means principally you're correct. The numbers may be changed here and there, but then that's a different story. But at least principally you're correct. Now, like I said, we can also do the same example without using table 56. How do we do that? How do I get the density of the liquid? This step is still the same. We find out the density, the gross standard volume. This step remains the same. Now, for second step is we find out that then instead of finding out the weight in vacuum, what we find out is what is the density in air. That is the density in vacuum minus 0.0011. What is the density in vacuum given by the surveyor?
0.795.
So do a very quick calculation now. 0.795 minus 0.0011. What answer do I get?
7939.
0.79.
7950 minus 0011. Okay, decimal 0011. That is 7939 tons per cubic in air. Now we already have density in air, is it not? The volume is already there available to us. Now, if a simple multiplication of these two, what we get is weight in air. So GSV into density in air, these two numbers, simple multiplication, what we have is 2003.010 tons in air. Which step is easier? This step or the one what we did before?
Second one.
This one, sir.
So in examination also, on board real life also, please use the second method. It is also more or less correct. You see the numbers are more or less matching. 2003.010 using this 0011, whereas 2003.077 using the table 56. So yes, you should know how the table 56 is used, but if possible, try to use this shorter method. Understood?
Yes, sir.
Yes, sir.
Okay. Any doubts in this calculations? I've used a very simple calculations. There is no complexities involved at all. So that you all understand the basic concepts of how do we convert from one unit to the other unit, and how do we go about doing this VCF and WCF. Any doubts in these calculations?
No, sir.
Density in vacuum, how do we get that, sir?
The density is vacuum is given by the surveyor. It is given by the surveyor. It is given by the cargo rep. It is given in the bill of lading also sometimes. In the BDN, if you're taking bunkers in the BDN, whatever the density, if the surveyor is giving you any density, the density is always in density at 50 degrees Celsius and in vacuum. Unless he gives you what is something else called a specific gravity and all that is different. API specific gravity, we're not talking about that because there's all beyond the MMD examination. In MMD examination, normally they don't ask you for this APIs and all. So if it's given density at 15 degrees Celsius, it is assumed it is in vacuum always. Even though it is not specified over here, it is assumed that it is in vacuum only. Yeah?
Sir, I have a doubt.
Yes, please go ahead.
Sir, I have never seen anyone using this table 56 for bunker calculations.
Yes.
Can you tell me the reason, sir? Is it because of the small?
It is not because of small, because in your Excel sheet or in the calculation, you already take into account density in vacuum minus 0011 I already get density in air.
Yes, sir.
So that is the reason why we even not only for bunker also, even for your normal oil tanker calculations, of course the alleged sheet it will be written very nicely over there using table 56 and all, but we don't go by that like what you call calculation of table 56. If your company has got that automatic table 56 incorporated into that in the Excel sheet, that's fine. Whereas for normal calculations, we don't even bother looking into table 56. Why? Because this also 0011 also gives you more or less accurate answer.
Okay, sir. Thank you, sir.
Okay. So that is why we have used only, we got this answer using only ASTM table 54, no 56. Clear? Now let's come, just give me another 5 more minutes because now that we've reached this stage, I don't want to stop it at this stage over here. Let's do a very simple calculation. This is towards like last calculations for the day. Now, this is my query now. We are going a little one step more complex, more advanced. We are going to talk about calculations on a cuboidal tank. The weight of the oil, we have to find out the weight of the oil. Now, weight of the oil is in what? In vacuum or in air?
In air.
In air. So again, weight of the oil, if nothing else is given over here, it is understood that we have to do it in air only. Okay, please take down these numbers, these values. Density at 15 degrees Celsius is given 785. The observed temperature of the oil is 27.5. Allege of the oil is also given. The tank dimensions are given. Now, for your ease, I'm also giving you table 54. The time starts now. Find out the weight of the oil in air. In the meantime, let me see if anything is come on the chat. Great. Anybody calculating?
Yes, sir.
And for all these calculations, please draw a small figure. That helps a lot. You will realize as to what is really happening. If you put a small like a figure like this and put the values inside, you will never make a mistake in these calculations. Anybody got the first step, that is the volume of the oil?
Yes, sir. 4891.095.
Okay, these figures are correct. We got height is 12.5, the allege is subtracted, that means the height of the oil is 11. So volume of the oil is 11 into 15 into 30.
4950?
Yes. 4950 cubics. The volume is very simple. This is what we did in the second, 6 standard, 7 standard classes and all. So please don't make a mistake in finding out the volume. I can still understand if you make a mistake in table 54, did some, even that's also not pardonable, but still that is understandable. But then please, for heaven's sake, don't make a mistake on these volumes. These are very, very simple calculations. Okay, now that we have the volume of the oil, this is at what temperature?
This is a 27.5.
27.5. That
We are
means
bringing
this is not
to
15 degrees Celsius. That this 27.5 volume is not good enough for me. So I have to get it to 15 degrees Celsius. So what table will I use for finding out this correction factor?
54.
54.
Table 54. So let's look at table 54, 27.5. Go across. Density is 785. So 785. We come to a figure where these two match. What is the figure?
0.9881.
9881.
That means now we have the volume also. Now we have the figure 9881 also. We have the density in vacuum. Using the same calculator in just single step, we can find out what is the weight in air. Of course, in the examination, it rules step by step. But what I'm saying is that in a single method, we can find out what is the end result.
3834.13.
Okay, so what we have is from the previous page, TOV is 4950, BCF is 9881. Find GSV. That is, multiply these two, 9881 multiplied by 4950. 4891 is the volume at 15 degrees Celsius. Is my calculation correct?
Yes, sir.
Okay, not bad. So next is step number 2, what is finding out the density in air. As you all already agree with me, density in vacuum minus 0011 is a more simpler, is an approved method. So don't worry about it. It's an approved method in the examination also. So directly we can find out what is the density in air. What is the density in air now?
0.7839, sir.
7839, correct. So not bad, my calculation is correct. Now the last step is to find the weight in air. We have the density in air multiplied by the volume, the standard volume. So what we get is the weight in air. So 3834129. Again, look back. The temperature is 27 degrees more than 15. The volume is 4950. So when I come to 15 degrees, what happens to the volume? Will it expand or will it contract?
Volume reduces.
Volume reduces. Has the volume reduced over here, 4950 to 4891?
Yes, sir.
Yes, great. That means this step is, at least principally, it is correct. Now, the next one is 4891, that is a volume. The density is less than 1. That means if I multiply by this factor, the weight will be much lesser than this value, which is here. That is 3834 decimal 129. Okay, so that is the final answer. That is 3839 decimal 129. That is the weight in, that's your answer for this question. That is, weight of the oil is 3834 decimal 129. Now, if you have a small element of doubt, why don't we try out this table 56 and see what answers do we get? So here is table 56. The step number 1 remains the same, GSV, it remains the same. Only the step number 2 and 3 changes. So what is it? What is the W? The weight reduction factor for this amount, this density of oil, 785?
Zero 0.99855, sir.
99855. Oh, I think I made a mistake over here. Okay, so my answer will not be very, but then even the factors are not so very great. That means there won't be an appreciable number. I think this red has come down a little bit. So let us see. From the previous page, there is no change in this calculation, 4891 decimal 095. Whatever we did for calculating the GSV is still the same. Now we go in a different path. We find out the weight in vacuum. What is the weight in vacuum? Weight in vacuum is directly multiplying this, multiply by this 785. That is 3839 decimal 510. Step number 3 is this factor is wrong by that in the fourth digit it is wrong, but let us see, it won't make a big world of a difference, but let's just have a look at it. So weight in vacuum is the weight in vacuum multiplied by WRF will give us the weight in air. That is, weight in air is 3834 decimal 326. There could be some changes in this decimal over here because my factor was wrong in the fourth decimal. Now what we got from the previous method was 3834 decimal 129. You see, the answer is more or less very, very close. And this much of approximation, this much of thing is acceptable for our examination. Is it clear? So even if you use it by table 56 or you use it by without using table 56, the answers are acceptable in both the cases. Is it clear? I saw in the chat there was one question from somebody. Why does the surveyor give us the density in 0.785? This is like the density in vacuum, not in air. But then see, now life can't be that simple. This is a small amount of work what we have to do. And as I said before also, all what the surveyor gets is from laboratory. Laboratory is from a standard temperature and standard in a very ideal condition. The moment he gives us the density in air, then we have to start talking about what is the pressure of the air, what is this, what is that, how much was this, how much of that, and all. So that gets into a lot of complications. So surveyor will not get into all these things. He will just give us a density in vacuum, which can be easily converted into density in air by us. So it's not a big deal at all.